Alright, here's a video for the 2.4 notes. We'll start by talking about the division algorithm. This is the examples that we did on the board. For example, when we divide, the pattern that we follow is to first identify what we are dividing into, and then we actually do the division, which is saying how many times does it go in, and then we have to multiply, and then finally we subtract. And we can see this when we're dividing numbers. For example, 7 into 10. I first identify 7 doesn't go into 1, so 7 has to go into 10. 7 goes into 10 one time, that's step 2. 1 times 7 is 7, that's step 3. And then 10 minus 7 is 3. And that gives me a remainder of 3. So I can write this as 1 plus 1/3. So I say 10 over 7 is 1 1/3. Or, whoops, off the page. I can also say that 10 is 7 times 1 plus 3. So those are two different ways that we can write our result from division. All right, so in example 1, we're reviewing polynomial division. And the first thing that we're going to do, we're going to split our area to write our division and our answer. So the question is asking 2x to the 4th minus x cubed minus 2 divided by 2x squared plus x plus 1. And in order to find this quotient, I need to remember the in and out rule. So 2x squared plus x plus 1 should be outside. And now my polynomial on the inside is missing some terms. I don't have an x squared and I don't have an x, so I need to remember placeholders. This is super important. Okay, so what I mean by placeholders is that there needs to be each degree represented. So 2x to the 4th minus x cubed, I need to represent x squared, so plus 0x squared plus 0x minus 2. And then we run through our division algorithm. So first step is to identify. 2x squared goes into 2x to the 4th how many times? X squared. Multiply, and that means to distribute. So 2x to the 4th plus x cubed plus x squared. And finally subtract. So that gives me 0. Negative x cubed minus x cubed. Negative 2x cubed minus 0 minus 1 is minus x squared. And then bring down my plus 0x. And then I start over. 2x squared into negative 2x cubed is negative x. And then distribute. Negative 2x cubed minus x squared minus x. And subtract. Okay. Now, personally, I don't like to leave the subtraction hanging out on the outside, so I like to distribute it in. So distributing the negative 1, this becomes positive, and every single sign changes. And now I'm doing addition, which is easier for me to keep track of. So this is 0, and this is x. Bring down my minus 2. 2x squared into x, it doesn't go in. X has a smaller degree, so this is my remainder. So remember, just like we were doing with our fractions above, this becomes a fraction plus x minus 2 divided by my divisor, 2x squared plus x plus 1. So here's my answer in fraction form. Notice it's got the fraction, and I'm taking the result of a fraction. So this is x squared minus x plus x minus 2 over 2x squared plus x plus 1. And that is fraction form. Our second type of answer we can write is polynomial form, where I don't have any fractions. And this is equivalent to multiplying through by the denominator. It tells me kind of the factored form of my dividend. So I have 2x to the 4th minus x cubed minus 2 equals my divisor, 2x squared plus x plus 1 times my quotient, x squared minus x, plus my remainder, x minus 2. Now the x minus 2 doesn't have to be in parentheses, but the parentheses help me identify it as the remainder. Okay, next we're going to look at the two really powerful theorems here, the remainder theorem and the factor theorem. And notice these only work when we're dividing by a linear factor, meaning degree is 1. So x to the 1st degree. I can't use these theorems if I have x squared or x cubed or anything like that. It has to be just x to the 1st power. And what the remainder theorem says is that if I'm dividing by this factor of x minus k, I can find the remainder without division by substituting k into f of x, so finding f of k. Now the factor theorem says if that remainder is 0, then it is a factor. If it goes in evenly, then it has no remainder and I can factor it. So in example 2, we're kind of testing these two theories. We're seeing how they work. So the first thing is to say x minus 2 would give me an x value of 2. If it's a perfect factor, it would give me a 0 of 2. So I'm saying, what does x have to be in order for this linear polynomial to be 0? And then I say, okay, now I'm taking f of that value, so f of 2. To find f of 2, I substitute it into f of x. So I have 3 times 2 squared plus 7 times 2 minus 20. And f of 2 should give me 6. Now, since 6 is a remainder that's not equal to 0, this tells me this is not a factor of f of x. So x minus 2 is not a factor of f of x. We can do the same thing in part B and C. Go ahead and pause the video and try that. All right, so we should get for part B that our remainder is negative 24, which means that it is not a factor. And part C, we have a remainder of 0, which means that it is a factor. So what this means is that I could factor f of x into x plus 4 times something. Or that if I had f of x divided by x plus 4, it would give me a quotient with no remainder. All right, the other type of kind of shortcut that we can use when we're dividing, again by only linear factors, is synthetic division. And synthetic division, similarly to the remainder and factor theorems, we're using the value that would make that factor 0. So I'm saying if x was 3, and I'm going to divide using the x value of 3. So we set it up like upside down division. I have my divisor, the 3, in the box, and then I have just the coefficients from each term in descending order outside of the box. And those are the numbers that I'm dividing into. So I've got 2x cubed minus 3x squared minus 5x minus 12. I didn't need any placeholders. And then a little gap and a line underneath. And the algorithm is that the 2 drops down. Whatever the first number is drops down. And then we've already done all the identification by writing out the coefficients. By changing from an x minus 3 to a positive 3, I've already changed from subtraction to addition. So I'm kind of simplifying this down to the 2 steps of multiply, divide, multiply, add. Multiply, add, multiply, add, multiply, add. So I drop my 2, I multiply it by 3, so 2 times 3 is 6, and then I add 6 minus 3 is 3. And then I multiply, 3 times 3 is 9, and then I add 9 minus 5 is 4, and then I multiply, 4 times 3 is 12, and 12 minus 12 is 0. Now this last number is always the remainder. Always, always for synthetic division, the last number is the remainder. Okay? How do I know what polynomial this represents? Well, this was an x cubed, and I was dividing by an x, so the result, x cubed divided by x, should be an x squared. So my result is 2x squared plus 3x plus 4. And each term just decreases by 1, because if I had any zeros here, they would be represented by zeros in my result, because I would have the 0 placeholders in my dividend. Okay, and that's why placeholders are so important. Okay, so I'm just decreasing the degree by 1 each term. Okay, so what does this mean? Well, it means that 2x cubed minus 3x squared minus 5x minus 12 can be written as x minus 3 times 2x squared plus 3x plus 4. That would be the polynomial form. And since the remainder is 0, I know it factors perfectly. Okay, so on the next page, we're looking at the rational zeros theorem, okay, which says that real zeros can be either rational or irrational. And if a polynomial has a degree n greater than 1 with integer coefficients, we can always find those rational zeros with the numbers at the front and back of our function. So we're going to apply that, but first, let's recall how we used to do this, okay? And we used to do it just by factoring. So if I'm looking at f of x in example 4, the way that we factor that is by recognizing it as a difference of squares, or a difference of perfect squares. So difference of squares has the formula If I have a squared minus b squared, it factors into a plus b times a minus b. So I need to know what was squared to give me my a and b. So what was squared here is 2x, and what was squared for the 9 is 3. So I know that f of x factors perfectly into a 2x plus 3 times 2x minus 3, and I could double check by distributing, by foiling, and I should get 4x squared minus 9 back. But what if my perfect squares don't look like perfect squares? So here I have x squared minus 2, and 2 is not a perfect square. However, it is a perfect square of an irrational number. I could write it as the square of the square root of 2. So here I could say this is x squared, and this is the square root of 2 squared, which means that I could write g of x as x plus the square root of 2 times x minus the square root of 2. Okay, so why do I care so much about factoring these? Well, by factoring them, I'm getting the zeros. The zeros are when this f of x would be 0. So when each factor is 0, it gives me a 0, which is also a root, a solution, or an x-intercept. So for f of x, I would say, what would make x 0? Well, 2x plus 3 is 0 when 2x is negative 3, when x is negative 3 halves. And we can see that the same process would happen here, except with a negative switched. So the zeros for f of x are plus or minus 3 halves. The zeros for g of x are plus or minus the square root of 2. Okay, we had a degree 2 function with 2 solutions. Degree 2 function with 2 solutions. Okay, so how do I get a list of all of the possible solutions if I'm looking at a function? So let's look at example 5 to see how do we apply this rational zeros theorem. Okay, well, in part A, we're looking at the coefficients. So our coefficient here is 1, and our constant is 1. And we're looking at the ratio. And by the ratio, I'm talking about the end over the beginning, 1 over 1. And we're looking at factors of 1 divided by factors of 1. Well, this is nice and easy because there's only one factor of 1, and that is 1. But I could have negative 1 times negative 1 as well. So that I have to consider the plus or minus version of each factor. So this gives me 1 and 1. And so my list of P over Q gives me the set of plus or minus 1. Okay, so what that tells me is if there is a rational 0 of f of x, it has to be either 1 or negative 1. Okay, but in order to tell if one of those is a rational 0, I can use the remainder and factor theorems. So I could say f of 1 should be 0 if x minus 1 is a factor. So to find f of 1, I say 1 cubed minus 3 times 1 squared plus 1. 1 minus 3 plus 1 is negative 1, not 0. So 1 is not a 0. F of negative 1, negative 1 cubed minus 3 times negative 1 squared plus 1. 1 plus 3 plus 1 is, negative 1 plus 3 plus 1 is negative 3, which is also not 0. So this tells me there are no rational roots. So how do I find the irrational roots? Well, you can always use your calculator to find them, and that's a good place to look in order to find your rational roots as well, but you need to know how to calculate them so that we can write our function in factored form. Okay? All right, in part B, change this to a plus 4. It will be easier to talk about what I want to talk about here. So in part B, we want to look at this function and find its roots, but first let's make a list of its possible roots, the numbers that could be rational zeros. Okay, so again, we're looking at the last number and the first number, and we do last over first. So we're looking at factors of negative 2 divided by factors of 3. Not just negative 2 over 3, but all of the factors. So what are the factors of 2? We have 1 and 2. What are the factors of 3? We have 1 and 3. So I want all of the numerators over all of the denominators as my options. So my possible list is, I usually just do top over bottom and then top over bottom. So 1 over 1 plus or minus 1, 2 over 1 plus or minus 2, 1 over 3 plus or minus 1/3, and 2 over 3 plus or minus 2/3. Sometimes you'll be able to simplify these, and we'll see some examples later where you don't have to list one of the options because it's already listed somewhere earlier. Okay, so here we actually have 8 options for our rational roots, but this is a 3rd degree, so obviously it can't be all of them. It could be at most 3 of them, but remember, we could also have irrational roots. So how do we know what numbers to test? I don't want to test all 8 of these, and that's when we turn to our graphing calculator. So on the calculator, you can graph your function, and what it tells you is it gives you an idea of where to start. And our goal, remember, is not just to find the zeros, but the purpose of finding the zeros is also to write this in factored form. So on the calculator, I put in the equation, remember with the plus sign, and graph it, and it shows me where my roots are. Now I can see by the hash marks that this is around 1, this is around -2, and that looks like maybe -1/3. So let's test those first. Okay. So it looks like maybe 1, 2, and -1, 1, -2, and -1/3 are the numbers that we wanted to test first, right? So let's start with 1, nice and easy. Let's find f of 1. 3 times 1 cubed plus 4 times 1 squared minus 5 times 1 minus 2. So we have 3 plus 4 minus 5 minus 2 gives me 0. It works. So now what? Well, this is where synthetic division comes in handy, because instead of having to divide f of x by x minus 1, right, because this gives us a factor of x minus 1, in order to find our new factors, I can just synthetically divide. 1 is the value of x that I'm testing or that I'm dividing out, and then I take the coefficients. 3, 4, -5, -2. Drop the 3. 3 times 1 is 3. 3 plus 4 is 7. 1 times 7 is 7. 7 minus 5 is -2. -2 times 1 is -2. Something happened. Oh, 7 minus 5 is a +2. +2, 0 is my remainder. How did I know? Because I was about to get a remainder, but I just said the remainder was 0. Okay, so this gives me a new polynomial, 3x squared plus 7x plus 2. Okay, well, I know that this new polynomial is a factor of f of x because I just factored out an x minus 1. So I have f of x equals 3x cubed plus 4x squared minus 5x minus 2. And now I can write it as x minus 1 times 3x squared plus 7x plus 2. But I need to keep factoring because this is not linear yet. So what number do I want to factor next? Well, let's try factoring in -2. Okay, so -2, and I'm just going to use my new polynomial to factor out because I really just want to factor out this new one, the quadratic part of my f of x. So here we go, and remember that was the remainder, so that's not in our polynomial anymore. Drop the 3. 3 times -2 is -6. 7 minus 6 is 1. -2 times 1 is -2. We get a remainder of 0. Amazing. Notice I skipped the step where I plugged it into f of x because I was pretty sure -2 was a 0 based on my graph. And also sometimes it's easier to just do the synthetic division than to substitute the number in, particularly if I've already factored out part of my function. All right. So this gives me a new function of 3x plus 1, which would give me an intercept of -1/3. So all 3 of those values that we saw in the graph turned out to be roots. Now, I didn't have to test all 8 numbers to find them because I used the graphing calculator as a resource. So this tells me that f of x equals x minus 1 times the newly factored x plus 2 times 3x plus 1. Okay, so now f of x is completely factored, and I can list my zeros as 1, -2, and -1/3. Okay, so why did I care? Couldn't I have just gotten that from the calculator? Sure, but could you have gotten the factored form from the calculator? Not as easily, because it's not an x minus 1/3 or an x plus 1/3. It's a 3x plus 1. Okay. Now you can also find that from the polynomial. We have an a value of 3, so I know I would have to have multiplied everything by 3, but we'll get into that a little bit more later. Okay, so in section 3, we were talking about how many times a graph can change shape, and we said it's important to know how many times a graph can change its direction because I want to know if I'm looking at the whole graph, all of the important parts of the graph, or if it does maybe another swoop later on outside of my frame. Okay, now we have a test that will tell us that as well, and that test is the upper and lower bounds test. So now we're binding, or we're looking at bounds for x values, whereas in the last chapter we looked at the bounds for the y values. Okay, so these are bounds for x values. And we're talking about bounds for zeros, and zeros are x values. So what this theorem says is that if I have a positive value that I think is my upper bound for the x value, then when I do synthetic division, all of the results should be non-negative, meaning positive or 0. If I have a negative value that I think is a lower bound, then when I do synthetic division, all of the results should alternate non-negative and non-positive. So kind of think of 0 as being a positive and a negative. It doesn't break our solution, but if it breaks the pattern, if I have a negative, 0, positive, then it wouldn't be a lower bound. So it has to be positive, negative, but if there's a 0, that's okay too. So positive or 0, negative or 0, positive or a 0, negative or 0, and so on for all of the solutions in the solution row of our synthetic division. So what does this look like? In example 6, we're looking for proving all of these zeros are between -2 and 5, okay? That doesn't mean there's a 0 at -2 or a 0 at 5. We're just saying they're within this interval, okay? So I want to prove that -2 is a lower bound, and I do that by synthetic division. So -2, and I'm dividing with the coefficients to the 4th, to the 3rd, squared, to the 1st, and constant, so I didn't need any placeholders. Drop the 2. -2 times 2 is -4. 7 and 4, -11, times -2 is 22. Minus 8 is 16. And then, sorry, it's 14. Yep, okay, 14 times -2 is -28. -14 times 2, this is a positive 28, plus 8 is 36. Okay, so lower bound, I want the signs to alternate. Positive, negative, positive, negative, positive. So we're okay. That works. They alternate. Positive, negative, positive, negative. Doesn't have to start with a positive. If it starts with a negative, they just still have to alternate. Negative, positive, negative, positive. And then I also want to test if 5 is my upper bound. So I'm synthetically dividing the same polynomial by 5. Drop my 2 times 5, add times 5, add times 5, add times 5, and then add. Okay, and I want to make sure they're all positive. Positive, 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 positive. We are good. So yes, this is bound. This is all of my zeros are between -2 and 5. All right, we're going to use this same polynomial on the next page, and we're looking at actually finding those zeros. So f of x equals leading and trailing. So I want all the factors of 8, which are 1, 2, 4, 8. All of the factors which are of 2, which are just 1 and 2. So I have my list P over Q. And again, I'm just going to start with all of them divided by 1, and then all of them divided by 2. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and then 1/2. 2 over 2 is 1. It's already in my list. 4 over 2 is 2, already in my list. 8 over 2 is 4, already in my list. Okay, but now if I look at these and I put them in order according to the number line, I would have -8, -4, -2, -1, -1/2, 1/2, 1, 2, 4, 8. And I know from example 6 that my solutions have to be between -2 and 5. So I can already eliminate 3 of my solutions. Okay? And now I'm going to look at the graph to see what numbers should I test first. Okay, so on our graphing calculator, we put in the function, we graph it, and then I'm looking at these zeros in comparison to my rational zeros list. So here, 1, 2, 3, 4, it looks like I have a 0 at 4, and 4 is on my list, so that's a good number to try. This looks maybe at 1.5 or 3/2, which is not on my list, so it's not going to be a rational 0 there. That's going to be irrational. That looks like -1/2, which is on my list, and that's like -3/2, not on my list. So I'm going to test 4 and -1/2. All right, so remember we were going to test 4 and -1/2. This is kind of my note to myself of what to test. So let's find f of 4. Okay, now this is really long. So finding f of 4 and using synthetic division on 4 will be almost the same amount of time. So I can save myself a little time by substituting or by just doing synthetic division. Or remember, I can also use my table value on my calculator. So let's do that. On my calculator, since I already typed it in here, second table, f of 4 is 0. Amazing. That just saved me from having to do f of 4 by hand. Okay, so I know it's 0, so that's the one that I'm going to start with, synthetic division. 4 divides into, and then the coefficients in descending order. The fourth, the third, the second, the first, the 0th. And I just say the degree so that I make sure if I need any placeholders. Drop my 2, times 4 is 8, gives me 1 times 4, -4 times is -16, and that is -2 times 4 is -8, gives me the expected remainder of 0. And then I'm also going to test my -1/2, -1/2, which I don't get from the table on my calculator because it only does integers. So I'm just going to go ahead and synthetically divide. Drop my 2 times -1/2 is -1, 0, 0, -4, 2, 0. All right, so now I have f of x. I can rewrite it in, so far, the factored form as x minus 4, and then x plus 1/2 times 2x squared plus 0x minus 4. Okay, so notice I need to factor this one still. X minus 4, x plus 1/2. I can factor out a 2, x squared minus 2, and we've seen this one before. X minus 4, x plus 1/2. Let me put the 2 in front. X plus root 2, x minus root 2. A nicer way to write this without the fraction would be to distribute the 2 into the factor with a fraction. So I can write this f of x equals x minus 4 times 2x plus 1 times x plus the square root of 2 times x minus the square root of 2. So now we have factored f of x, and we can write its zeros as 4, -1/2, and plus or minus the square root of 2. Okay, example 8 combines example 6 and 7. I'd like you to try that on your own. Pause the video, and I'll put the answer. Okay, by typing the equation into the calculator, we get a graph that looks like this, which recommends our bounds to be maybe like 0 and 2. Remember, we can't have a lower bound that's greater than 0. It has to be non-positive. It has to be less than or equal to 0. So let's test our bounds at 0 and 2. Right, so for 0, we have to the 5th, to the 4th, I need a placeholder, cubed, need a placeholder, squared, 1, 0, 10, 0, 0, 0, 0, 0, -3, 0, 1, 0, -6. This one's positive. Those are 0, doesn't matter, negative works, positive, negative. So 0 is a lower bound. Okay, so then we need to test 2 to be an upper bound, 10, 0, 0, -3, 1, -6. 10, 20, 20, 40, 80, 77, 154, 155, 310, 304. Those are all definitely positive, okay? But I'm not sure that 2 was the closest upper bound. Let's try 1. If I try 1, 10, 0, 0, negative 3, 1, negative 6, again, 10, 10, whoops, 10, 10, 7. So 1 is also an upper bound. So I know my zeros are between 0 and 1. This is my bounds. And then I need to find the actual zeros. Okay, so I have 6 and 10 are my P and Q. But let's look at our graph. It looks like it might be at 1. That's our only rational zero. That would be really close to 1. Okay, so I'm looking for a rational zero really close to 1. It's not going to be 2 or 6 or 10 or anything like that. So when I'm looking at my rational zeros here, my list of rational zeros would have to be factors of 6 divided by factors of 10. Okay, hopefully you wrote this list. It's about to appear now. And we can eliminate anything that's not between 0 and 1. So none of these. This works, but not the negative. That would work. That would work. Oh, that doesn't work. That works. That works. That works. That doesn't. That doesn't. Oh, and I wrote 6/5 twice. Okay, so we're already narrowed down to 1, 2, 3, 4 options. It was more than a half. It was more than a fifth. So, and it was more than 2/5. So maybe it was 3/5, but it doesn't really look like 3/5. So let's go ahead and use the calculator to second calculate the zero and see what you get. All right, so you should get that your zero is around 0.95. Notice that was not on our rational list, so it is an irrational root. And what that means is that all of our other roots are either imaginary or perhaps this irrational root is repeated multiple times. So the only real root, x equals 0.95. All right, don't forget to write your summary and reflection.